computer, and then I will share my screen. Okay, so you are seeing, I think, a lot of things. And then I will put this in presentation mode. Okay. So as always, thanks a lot for joining us today. Oh, here it should say day 4. Let me change it. Day 4. So thanks for joining us today. Today we will move to inversions with SER. I think it's a bit long topic, and I want to go as slow as before. So I thought that it could be better to divide this topic into tutorials, and maybe I can make it shorter than 90 minutes, although let's see. And so the idea is that today we will focus on the basics of inverting a synthetic profile. So it means we will create an atmosphere, we will use it for doing synthesis, and then we will invert the synthetic profile that we create from that atmosphere. And we will do that with, yes, sorry. Sorry, as I said before, and on the courses, everything that we do with this step is essentially the same that we will do for desire. So if you get familiar and you understand the process that we will explain today, it's something that you will then repeat later with desire, because it's essentially the same. I forgot, so this is also something that I will talk about today, and is that for performing inversions, it's important to choose a proper atmosphere. I will show later why. Some of the things that are important to keep in mind is the number of optical depth points, and also the properties of the atmosphere. So the stratification of the different atmospheric parameters and the values that you choose. I will show you some examples, but the idea is that I will start first with these recommendations, and then we will go to inversions. And this is what I was saying. So we will invert synthetic spectra. We will start with very simple, a simple example where we take a foul atmosphere. We add magnetic field and velocity, and then we do a synthesis, and then we try to invert that to fit those profiles and recover the initial atmosphere, starting from a different atmosphere. You will see that this is very easy, and it's easy to follow, and the code will reach almost perfect results. And then I will do the same, but using one pixel. I have 3, but we'll focus on 1. Pixels from Muran Sunspot, presented in REMPEL 2012. And in this case, it's completely the opposite. So the atmosphere is extremely complex, and you will see that the code will struggle a bit to try to fit the profiles. And I think in general, observations will be in the middle. So probably will be not as easy as the synthesizing with a full model, but probably not as complex as what we have from simulations. So you will see that I will try to show you today the extreme cases, the simplest one that is easy to follow, and then a complex one that you will see that it's difficult to really obtain a perfect fit. So then I think, yeah, that's all. So we go to the code, and then have here. So so then let's start with this program. So as always, I will cover them here, and then I will put them in Dropbox, so you can download the programs and repeat the examples. And as I said before, so the first thing that we are going to do is to create a synthetic profile, because in general, when you are working with observations, you have your data, that is the Stokes profiles, you know the information about density, Q, U, and V, and you know the wavelength. So you know already which profiles you want to fit. But for this example, we are going to create first the profiles, and then we will try to invert them. So then I will pick a file model, and then as in the previous class, we are going to create an atmosphere. In this case, for simplicity, I'm only going to add a magnetic field. velocity, inclination, and azimuth, and I will leave the rest of the parameters unchanged. So then we will just focus on inverting these 4. And I'm creating them with a line of sight gradient. So I think, let me call this. So if I do plot tau and field strength, you will see that is a magnetic field that in lower layers, in log tau 0, -1, it has a larger value and then it's decreasing with height. And I'm just putting the same values for similar stratification for velocity or inclination. So it's something that is relatively smooth, but it has a gradient. So the code needs to try to fit the profiles reproducing this behavior. Okay, so then the first thing we do is we write this atmosphere that it comes from the file model. And then as always, we call ser, and we tell the code that it should run this control file. So if we go to the control file, what we are doing is writing a synthesis. So we have a 0 here. Then we have the same exact files as before. So here we have the spectral range that contains the 2 ion lines. Then this is the information where the code will look for the spectroscopic information, anatomic information, abundance, and then the atmosphere. The code is using for creating the files. So this is the one we create here. You can see that this right model is creating the scene.mod. And then the code, it will use this atmosphere, and then it will produce output that will be these profiles. Okay. So then these profiles, I will just read it here and I will plot them just to show you how they look. So it's again a Stokes I in this case, and you see 2 lines, and you see that there's some, so the wing is more bended, if I can use this word, because there's an asymmetry. So when you have asymmetries along the line of sight, the line is not symmetric. And if you plot, for example, Stokes B, you will see the same. So these profiles are relatively symmetric. Okay, so now we have the profile, and then what we are going to do is create an atmosphere that we will use as an initial model for doing the inversions. So then for simplicity, I'm going to take the same file model, but then I'm going to put a constant magnetic field of 500 Gauss, a constant velocity of 1 kilometer per second, an inclination also constant with height of 30 degrees, and then 70 degrees of azimuth. And then the idea is that after that, we will run an inversion. Okay, so, but before, let's make a stop here. Okay, so the idea is that the inversion will be done calling ser, but in this case will be a different control file for simplicity and for allow you to keep things separated. That will be this one. Okay, so in this case, the number of cycles is larger than 0. So we are telling the code in this case to run 2 cycles. We are telling the code to invert the file profiles.per that was created in the previous step. So this is now input for this step, and before was the output. We are using exactly the same values here, and we are using a new atmosphere. It's called init from initial atmosphere, and we have created here. So we took the file model, so we are keeping the same temperature, same electron pressure, the rest of the things, but we are starting from a different magnetic field and velocity. Okay, and then we have here weights and nodes, but before getting there, because the number of points that we will use here will depend on the atmosphere that you choose. So let me just try to explain what I said about the atmosphere we would choose for starting, and then we will get into this. So what I mean is, and I think I'm getting stuck. So what I mean is that when you want to do an inversion, you can choose the number of nodes that you will have with height. But this number of nodes depends on the number of divisors that you have on your number of optical depth points. So this sounds a bit strange. So I prepared an ideal program that I will send it to you. It's here. And there's an explanation how to run it and what it does. It's very, very simple, but it's the way of knowing how many nodes you can have. So the idea is that imagine that you have an atmosphere with 60 points in optical depth. So if you type node 60, it will tell you that with this atmosphere, the code can only use one node, two node, or 60. So even if you try to perform an inversion with 3, 4, 5 nodes, the code will always pick 2 because it cannot pick more than that. So then it's important that when you create the initial atmosphere that you will use for the inversions, and this is both for SER and design, you should have an atmosphere that allows you to have a wide range of nodes and the nodes that you want to use. So for example, if you use 61, you can see that now the code will be able to use 1, 2, 3, 4, 5, and a lot. Okay, so it's important that you keep in mind the number of rows that you have in your atmosphere. I mean, the number of optical depth points. So for example, in this case, the file model that I'm using, this one, it says that it has 82, but be careful because the first row is the microturbulence, filling factor, and straight light. So it has, in fact, 81 points. Okay, so if you type print 81, sorry, sorry, nodes 81, it will tell you that with this atmosphere, you can choose between 1, 2, 3, 5, 6, 9, or much larger values. If you wrongly remove one row, then you are stuck in 1 or 2 nodes. Okay, so in general, we always have in the database atmospheres that you can use for having a lot of nodes, but it's also important that if you create your own, just be careful to keep in mind that you should have some specific optical depth points in order to have then the possibility of adding nodes. And then the second thing is that if you remember, just let me close this one. So if you remember, I did the synthesis with a gradient along the line of sight, but I'm going to start the inversion with a constant magnetic field and constant velocity, inclination, and azimuth. So there's no rule for that, but my impression is that it's always better to have as an initial atmosphere, even if you have different ones, because it's sometimes better, and we will cover this in the future, but having them with constant stratification, because some atmospheric parameters, they are defined positive, for example, microturbulence, field strength, inclination. So if you start an inversion with an atmosphere that has a constant magnetic field, like this one in black, and the code needs for some reason to reduce the magnetic field, like, I don't know, 500 Gauss, it will just move this line down, okay? If you start with this black one, and then the code needs the same, because, for example, the magnetic field here is around 500 Gauss, then the code will move all the line down, because you usually start with one node, so it's just up and down. And then if you reach this, then the code, as magnetic field strength is defined positive, it has to put 0 values in all this range, okay? But after that, in following cycles, the code will not move this region from 0 because it cannot perturb atmosphere that is 0. So then you can force the code to have a wrong result if you are starting with an atmosphere that is really far from the one that you need to obtain. So in general, a constant magnetic field, it's always relatively stable. So my advice is, in general, you can try something like this, but I would say that the safest thing is to just define an atmosphere with constant magnetic field, inclination, velocity, and the rest of parameters, except temperature, because temperature usually you need the stratification. So these are the two things that I recommend you before doing an inversion. So keep in mind the number of nodes. So I mean the number of optical points. So then you can have a given number of nodes. And then I would say that start with simple atmospheres. So then the code is free to choose any option, and you will not force it to have this complex scenario where then the code will only change this part. Okay, Basilio, if I say something wrong, just jump in, okay?
Yeah.
Okay, but so far so good, right?
Yes, yes.
Okay. So then we have checked that we have the proper number of optical depth points, and then we have a simple atmosphere. So now let's remove this, and then yes. So now we are running the inversion, and as I said, we have to provide information on weights and then on nodes. So let's start with nodes first. And for now, let's forget about this selection of automatic nodes. I will cover it later. So just focus that we have 0. So then the code will really follow what we write here. And then we are saying that we don't invert temperature and electron pressure because we keep it the same. And we are going to invert the magnetic field with 1 node and then 2 nodes, and then 1 node, and the same for all the parameters. So it means that the code will run twice. In the first iteration, it will move up and down the total stratification. And then in the second cycle, it will be able to change what we have in the extreme of the atmosphere. And then it will interpolate in between those optical depth points. Okay. And then we have weights. The idea is that the code will compute in a given way that I will try to explain you next week, a chi-square value, okay? And this is essentially the difference between the target profile and the one that is produced by the synthetic code. I mean, when we run the code. So then after doing one cycle, the code will see how different the profiles are, and then it will try to change the atmosphere to try to match the profiles. But sometimes in general, Stokes Q, U, and V, the signals are always a percentage of Stokes I, and in general, a low percentage. So it means that in general, the errors that you will have in Stokes I can be an order of magnitude larger than the errors that you could have in Stokes Q, U, and V. But sometimes so I mean, because the amplitude of the Stokes signals is much smaller than I. But the idea is that you need to fit Q, U, and V if you want to have information about the magnetic field. So one way to tell in the code, I know that the error in Stokes I is larger, but still I want to really focus on Stokes Q, U, and V, is to provide more weights here. So then if you said, for example, we put a weight of a Stokes B of 10, then you are telling the code that the importance of the error in Stokes B is 10 times larger than the error that you have in Stokes I. So even if the error in the Stokes I is 1 order of magnitude, you are compensating that, and you are telling the code, I know that the Stokes I is not so good, but still, I want to have Stokes B because I'm interested in the magnetic field. So then with this, you can really put more emphasis on different parameters, and then the code will try to do its best. Just as advice, I think there's no clear recipe of what values you need to have there. I think you should try a bit, and it sometimes depends mainly on your observation. But it's true that most of the times, if you want to have a good fit on the Stokes Q, U, and V, you need to put more weight than Stokes I, because then the code will not be able to fit them properly. Okay, so in this case, I'm just let's put 2. So I'm telling the code that you should check the errors on Stokes I, but also Q, U, and V. But in this case, I'm giving more weight. So the errors will be in principle more important than those on Stokes I. Okay. If there is any question, just let me know. If not, I will try to show you later a bit more about that. So then we have our configuration ready. I think I'm not changing anything here, so we can keep it simple for now. So then I'm just going to run this part. And then let's stop here. So just let me check that the code runs. Okay, so it's doing an iteration, it's printing some things that are related with the chi-square and other parameters. So if you want to know more about that, we can check. You can check the manual or you can ask us. But the idea is that it finished. It's saying that it's a version of April, but it's just because Basilio sometimes takes time to update this information, but the version is newer. But the idea is that it finished. It says end of cycle 2. So then the inversion was done. So now it's what has happened. So we have here profiles.pair, and then we have the atmosphere. So then this is really important. So we have that the code will generate some files in your folder, and they are related with the name of your atmosphere. Okay, so I'm putting here some text. So what I'm saying is that the code will produce first two profiles, the one from the first cycle and the second for the second cycle. And these will have a name that is init add, and then a value, 1 or 2, depending on the cycle. And then the extension will be pair from profile. Okay. Then it will also generate two atmospheres, one from the first cycle that produce the profile init add -1.pair, and a second atmosphere that it produced the profile init add -2.pair. And it will be the same. So init add -1 and -2, but in this case, .mod. Okay, and the final files the code will also provide are the error. Sorry, this should be error. So it's the same name of the atmosphere, the number from the first and the second cycle, but then the extension will be error. Okay, so if I go to the folder, you will see that we have init-1 error, mod, and pair, so atmosphere and profile, the same for the second cycle. Okay, so now let's check how the inverted profile looks like. So now we have run the inversion. I'm reading the profile of the second cycle, and I'm going to plot, in this case, the input profile versus the fitted profiles that will be in red. Okay, so if I do this, then what we have here is black is the original ones, I mean the target or like our observation, and red is the fitted profile. So you can see that in general the fits are really good. And sometimes when you look at the profiles and the difference, just be careful that you should also take into account the amplitudes. So in this case, if you look at Stokes Q, you could say, oh, it doesn't look so good. But if you see it's more than 10 times smaller than, for example, Stokes V. So sometimes if you have very, very low signals in one of the profiles, it's okay if it's not so well fitted. The important thing is that in general, you have a good fit in all the profiles, and the one with larger amplitudes will be also very well fitted. So, but in general, I would say that this is a very good fit. Okay, so then now let's check how the atmospheres look like. And in this case, I wanted to do it very detailed. So what I'm going to do is I'm going to read the atmosphere that we use for the synthesis. This is our goal. Then I'm going to read the atmosphere that we use for starting the inversion. This is our starting point. Then the atmosphere that the code obtained after one cycle, and then the atmosphere that the code obtained in the last cycle. Okay. So I have colors here. I forgot to say, sorry. You will have in day 4, you will have high quality figures of everything that I have done. So for example, the one that we are seeing now, I made it in high quality. And in this case, I put it labeled, so it will be easy for you to distinguish what is observed and fitted. So don't worry if you don't see some labels now, you have them in the folder. So what I was saying is now we will have 3 different colors. So let's try to run it. So we have this. The initial atmosphere that we are starting the inversion from is the blue one, okay? Then the first cycle is orange. So then, for example, for velocity, the code moves from here to here in the first cycle. Black is the goal. So you can see that is matching the black line around lockdown -2, -1.5 that we saw last week. That is a region where the lines are very, very sensitive to the atmospheric parameters. So the code is matching more or less here, the atmosphere. And then in the second cycle is moving this point up and then this point down and is producing the red one. So we started in blue, moved to orange and then to red. And you can see that the red one is very, very, very close to the black one. There are some difference mainly in these layers, but as we saw last week, is because essentially the lines are not sensitive in this region, so the code cannot really decide if should be a bit up or a bit down. And the same is happening for all the parameters. So the code starts from a point, then it moves up. It tries to match the atmosphere, the black one, at around lockdown -1.5, -2. And then it perturbs one side and then the other side. And then you can see that the code it's really almost matching the original one. Okay. Again, as I said before, you could see later in more detail, and also I put it here, the labels that I forgot to put it here in that part, but you have it here. So later it will be easy for you to check what is doing the code in each step. Okay. So then we have that now we have the profiles. We see how the code moved from the initial atmosphere to the final one. And now the last step that we are going to take is we are going to read the error the code provides for the last atmosphere. That is the one that we believe is the best one. And then we are going to do the plot that we probably should do when we are doing a paper or when we are presenting this to someone. So in this plot, what we are presenting is black is the original one, red is the atmosphere that the code obtained in the last cycle, and then error bars are the error that the code is providing for this atmosphere, for this solution. Okay, in this case, as the atmosphere is very simple, don't think too much about the errors. Later, you will see that they are more like the ones we saw last week for the response function. But this is the main idea that I wanted to show you for the simple case. So first, define a proper atmosphere, then try to fit the profile. Then when you have done the inversions, check the profiles, compare them. After that, also check the atmospheres. And finally, add the errors to the atmospheres. So then you can really say where you have your region of trustworthy range. Okay, so I will now going to do almost the same, but with more complex atmospheres. So do you have any question until this point? Okay, so then I will I will also put a second folder called Atmos Invert 2. And the idea is that in this case, you will have inside the folder is this one. You will have 3 atmospheres. They are called with index points. And those points, they are pixels that you can see here. Okay, so I took the sunspot simulation that I mentioned before. I took the original one that is in geometrical height and we have gas pressure. I transformed it to SER format. And then I saved 3 pixels. One is around here, that I think this is like a network patch. Then another one is here, that is like a penumbral filament. And then we have here that is something like umbra. We will learn how to do this in, I think, in 2 classes. But the idea is that I already saving atmospheres that belongs to very different regions in the simulation. Okay. So then we will start with this one. That is what I think is a network patch. I will go through the program that is essentially the same one as before, but I recommend you to try later to play a bit with the other atmosphere. So they are there so that you can play a bit. Just before I forgot, because I forgot before, I said here in this point, after the first inversion, I said you can play a bit with the profiles. So you should also try this, not only playing with the number of, the weights. So you can play with the number of nodes, but also try to play a bit with this simple example, to play with the weights that you give to Stokes I, Q, U, and B, just to get a feeling of how the inversion can be better or even worse. So if you give, for example, a lot of weight to Stokes Q that is much smaller than V and U, you probably will get a better fit of Q, but maybe your error in Stokes B is much larger than the one that you had before. So just play a bit and always check if you are really going in one direction or improving, or in the other direction that will be a worse fit. Okay, so then let's start with this one. And in this case, I'm going to do the same. So I'm reading the atmosphere. In general, I just wanted to keep the same format. So before we read the atmosphere, we did some changes and then we write it as a scene.mode. But in this case, the atmosphere is already complex. So I'm just reading it and then saving it as a scene. So then we can just use the same script. Okay, so let's make a stop here. And then I will just leave this one. I go to Atmos, Invert 2, then run the script. Okay. So in this case, the profiles, they don't look so complex. So that's good, but you can see that it's not exactly that. But let's go ahead. So now we have synthetic profiles. And again, the output of this synthetic synthesis is going to be the input of our inversion. Okay, so these profiles are going to be the profiles that we want to invert in this case. So as before, we are starting with exactly the same atmosphere. It's a FAL model where we keep the temperature and we add a constant magnetic field, velocity, inclination, and azimuth. And the rest parameters are basically the FAL ones. Okay, and we run the inversion, and I have a stop here. Okay, so just let me save this. Okay, so now it's a bit different. You can see that profiles are a bit complex with asymmetries and complex behavior, and the code is trying. I would say that the fit, it's okay, but it's not as perfect as before. So, but in general, what I'm doing, and I forgot, is that it's a bit complex. So I just use another cycle, 3 cycles. And I'm playing a bit with the weights, but as again, you can change them. And I'm adding more freedom. So now it's not linear gradients. And now you have 1 node, 2 nodes, and then 5. So the code can in fact introduce some fluctuations, and the same for temperature. So it can change the temperature in different heights. Okay, but please feel free to change them and play and try to get a feeling of where sometimes you can add more flexibility and then it will improve the results, and where it doesn't change too much, so then it's probably not useful. And then it's okay, but let's check the atmosphere and let's see why the code is struggling to obtain a good fit as before. Now is the same process, although now I'm adding a third atmosphere because we have 3 cycles. And then I put a note here. So we're inverting the temperature. So then in principle, you should also check that the temperature, the fitted one seems is close to the original one, but I'm trying to keep the same format as before. So I'm just plotting velocity, field strength, inclination, and azimuth. But you should check also temperature and play a bit with that. So we have 4 colors. Just let me go back before just checking. So just keep in mind that I put it here, the labels. So black is the goal, the atmosphere that we should obtain. Blue is the starting point. Then orange is the first cycle. Red is the second cycle, and green is the final cycle. Okay, so then we can discuss, for example, this one. So the code is trying to get velocity that you can see that the original one is doing some complex pattern, but it's more or less following at the end. And here it goes a bit further, but I think the sensitivity in this point is not so high. But the code is trying to match as before between -1, -2. You can see that the code is always in every cycle. In the first one with the orange line, in the second one with the red one, trying to follow this, and then with the green one is still following this, but also is getting closer to this point. So you can see more or less, and you can play, but how the code tries slowly to get to the solution. The same with the field strength. So we started close to this point, but here the lines are not sensitive. So then the code move a bit high here. Then it tries to do this, and then it tries to at least have some kind of from low values to larger values and then go down. So it's trying, but I think it's really a complex atmosphere. And in the case of inclination, it's not so difficult, so it's not so complex. So then we start from a 0, I think. No, from this one, it moved it down, and then it tried to do like this, and then finally it just does like this. Please just keep in mind that in general we are not sensitive in this region. So basically the code it's behaving well. In the case of the azimuth, it's really a complex azimuth because it's changing from 100 to -100 degrees with height. So it's really a complex azimuth. But again, here we are not very sensitive to the azimuth. So then the code is trying its best, and you can see that it's obtaining an average value here. Okay, there's something that I will send you later because I think I made a mistake, and I'm discussing this with Basilio because I think the code will provide an azimuth that goes from 0 to 360 degrees, but the original atmosphere that I'm giving the code, it can have a negative value. So I think the atmosphere that I'm using goes from -180 to 180. But the inversion is working from 0 to 360. So I think I will try to talk with Vasily about this. But I think maybe I should change this value to plus, say, 180.
But it's the same. Just it's a representation thing because 180 is the same.
Yes.
That 180, okay?
Yes. Okay. Yeah, so Ryan is saying that sometimes he gets negative azimuths from inversions when initialization goes between 0 and 360. So I think, Ryan, yeah, I think we need to check that because what Basilio is saying is that, so internally the code, it doesn't see any difference. And I think at the end, we are just changing that. And maybe we can do it in a different way. But essentially the code, because of the ambiguity, 180 degrees ambiguity, it's probably exactly the same to have -180 than having 0 or to have 180. So then sometimes it can get a bit crazy. So in general, be careful with the azimuth. I think I will work with Basilio a bit about that just to be sure. Yes. So you're seeing the chat, Basilio? Are you seeing my chat? So
no,
Ryan,
okay.
Yes. So Ryan is asking if the code internally use sine and cosine, and yes. So for this reason, the final value it can be
exactly.
Okay. But the idea is that later, in general, we should apply an external disambiguation of the 180 degrees. And this is because SER doesn't do that. So later on, you should, yes. So later on, we should apply some disambiguation if we are using, for example, transport or something like that. Okay. So then just keep that in mind, that the azimuth, it's complex in this case, but also I think the code sometimes can go from 180 or minus 180. So just be aware of that. But in general, this is the problem. It's a complex atmosphere. So the code is trying, but it's not getting there. Although I would say that it's okay. And then let's go to the last step. So now I'm going to read the error of the third cycle, and I'm going to do the final comparison. So in this case is we will have the target atmosphere, that is the black one, the red atmosphere, that is the one from the last cycle, and then you have the uncertainties. And in this case, you have the uncertainties that you will always, well, in general, have. So these are more realistic in the sense that the lines, the response function of the lines above -3, 3.5, they started to decrease very, very quickly. So then, for example, inclination, it's saying that the uncertainty is so high that you probably, or you should not be too confident on these values or these values. But you can see that they become very, very small around -1.5. And this is the reason that we have seen the code always try in the first cycle to get a good result in this value. So for this reason, the constant stratification was always close to the target atmosphere in this region. Okay, so this is what you can, you in general will have when you have an inversion of some observation. It will look like this. So you will have an errors that they are large in the extreme, in the edges of the atmosphere, on the top and low boundaries, and then they will be relatively small in the middle part. And as we said in last week, so if you have spectral lines, additional ones that form in -4.5, I mean, they are sensitive in -4.5 or -5, then these uncertainties will also decrease. So then you can have better results, but also a more reliable results. So then I think I wanted to keep things shorter than general. So the idea is you can just change this name and then put here, for example, this pixel or this pixel, and you will see that the code will have a different result. The atmospheres are different. And then you can play also with the weights and also the freedom of the atmospheric parameters, the number of nodes. But in general, it's going to be the same step. So I prefer to just not do it and let you try it at home. So before going back to the presentation and the things that I recommend you to try, is there any additional question about the process that I followed today? Again, you have the high quality figures here, so you can check them later. But is there any question until now? Okay, so then let's go back to the presentation, and then as a recommendation to do during the following days is to run the test that I showed today to check that everything works and you understand the process. Here, I think you can play a bit. You can, instead of adding only a linear gradient along the line of sight, you can change you can change the magnetic field velocity and try to reproduce. Then try to invert the mutant pixels. I think you will see that it's not very easy sometimes to obtain very good results with a given configuration with pixels from the umbra, from the penumbra, and the network. So sometimes you should try to have a standard configuration, and maybe in some cases, if it doesn't work, then you should invert small patches with a slightly different configuration. That could happen if the atmosphere is completely different. So try to get an idea and see if you can fit with a configuration that you understand the 3 different pixels. But it's important, and I think this is something that I want to say, and I want to say it in some kind of a joke, is that it's going to be really difficult to match them. But I would say that in general, the sun is not as complex as simulation, but it's some kind of a joke. No, it's just that in general, yeah, I think simulations are much complex, but those line of sight, complex variations in short scales, I think it's going to be not so easy to obtain them in observed profiles, because you probably need a lot of spectral lines for that. So if you cannot reproduce all this variation, I think it's okay, because in general, observations will probably, so we will fit them. You can see that we fit them reasonably well. And the code does not need to add all these gradings. So it's just that I just wanted to show you some example of complex atmospheres that are realistic because they are from simulations. I didn't create them, and how it's difficult to for the code to embed those atmospheres with only 2 spectral lines. Okay. So Basilio and Han, do you want to add something?
Well,
No.
about the complexity, I mean,
Yeah.
Yeah.
no, yes, I think these simulations are a good representation of the complexities that you'll encounter in the sun, and so there's a good illustration of how difficult it is to actually match.
I think that perhaps if you allow for more number of nodes, more complexity, you can get a better result. For instance, if you allow for automatic selection of nodes, maybe in a posterior cycle, maybe, or you are starting from a different gas atmosphere, from a different initial atmosphere. Sometimes you can.
Yes, so I forgot about that. So what Basilio is saying is that here we have 1, so I mean 0, and the idea is that you can put 1. So then what we are saying here is that the code will be, so it will take from the maximum number of nodes, it will take the maximum or a lower value. So imagine that if the code is running this cycle, but the previous one is already providing a very good result, instead of taking the 6 nodes, it will probably take maybe 3 or 4. So it is not taking all of them, but at the same time, you can put here like, I don't know, 12. I don't remember if this was allowed, but imagine 12. So then the code will decide if it will take this 12 or maybe 9, and then it will allow for an extra flexibility, and then maybe the results are better. So the idea is that I would say that at least try forcing them. So imagine that you said, I'm going to put more cycles. So remember that we were, I think, nodes 81. Yes. So you can have 6, 9, 11. So maybe you can go temperature until 9. And then, for example, here you can put 6 or maybe 9. And try to check if this improves. And also after that, you can try to check if you put 1 here, if the result is better. So the idea is that you should experiment. It is true that I'm a conservative person, so I try to keep the number of nodes as low as possible, but Basilio is a more relaxed guy, so he always try to put a lot of nodes and then check if it works. So you should try both options. I would say that if you have a standard configuration with not many nodes, you can guarantee that even if the result is not so good, it will always be relatively good. And in the other case, if you put more nodes, you will have in some cases very, very good results. But in other cases, you can have that the atmosphere is maybe too complex and the code it's not obtaining as reasonable results as the one you can have with not so much freedom. So I think it's up to you. Just play and try to get a feeling. And later on, when we start doing parallel inversions, then you will have for example, the snapshot that I show you, this one. So then you can say, okay, I'm going to invert these 200 times 200 pixels, and I'm going to try with a lot of nodes or just a few nodes, and then you just compare the results, and then from there you will get a feeling of when you should go for more complexity or less complexity, and how the codes behave. Okay, I think there was a chat.
Even you can put 0001 in the automatic selection, then the first cycles are fixed and the last one is free. And even in the number of nodes, you can put 2, 3, 6 star, and then a star means that the code select how many nodes it likes.
Yes, yes, and in this case, a star will be all these numbers, including 81.
But as a maximum, okay? But the code run please, because the code will choose 6, 9, no more than this.
Yes, so let's keep it like this, and then asterisk, asterisk, asterisk.
No for azimuth, no for azimuth, no. Okay.
Okay. Okay, invert. So let's, oh, sorry.
You need to, okay. Okay.
No, I just wanted to put here in a stop in the atmospheres, because I think here, no. Yes, here, just to check. And I'm just running 3. I didn't increase the number of cycles, so let's check. So we are more or less where we were before. So I think this is good. This is now fluctuating, and this is okay, good. And then again, we have some fluctuation here. And then the azimuth, I think we didn't change it. And here we have probably a better fit here, I think. And here was more or less okay. So yeah, I think we should experiment. But the only thing is that my concern about using too much nodes is that we are interpolating between nodes and we're using splines. It's set here at the end. So where is it? Here. Splines, it's the default. And these sometimes can introduce this wavy pattern. So I think as a recommendation, try both. Depending on your pixels, and be aware of this. If you start to see this wavy pattern, then maybe you have too many nodes. But if you see that the fits are better, so then it's maybe worth it to keep some freedom. But just try to find your style. I think Basilio is more flexible than me. I tend to more conservative. Okay, so then just keep that in mind. So you can play with the selection of nodes. You can, so in this case, what we have done is that we don't want automatic selection of nodes in the first cycle. So then it means that it will pick the number that we have here. In the second one will be the same. And then we're telling the code that in the third cycle, it can take any number of nodes the code considers that are necessary. And if we put an asterisk, we are also saying that the number of nodes that can be used there are any value that is included in this with this configuration. So it could be 3, 2, or it could be 11 or 17. Okay, so just this is a good thing that I didn't include in today's class, so it's good that Basilio mentioned it. And just let me keep this.
If you look at the screen at the output, you can put the cycle. You can see the number of nodes that it's choosing at each iteration. This number now means that, and it's taking 11. I don't know. Is temperature?
Where?
Okay.
So let's see.
In velocity. Okay, this is the first number is temperature. Okay.
Yes. So temperature, then field strength and velocity. So let's.
Then it's changing from.
Yes. So velocity, it took 17, 11 for magnetic field, and 11 for temperature.
In the last iteration, but he was changing that. Okay.
Yes. Okay. So just keep that in mind. I think for me, the important thing of inverting is that you should try and you should find what works best for you and for your type of observation. And there are some general rules, but I think they are not fixed. So you should experiment and try to keep always things in mind, like the fit should be good, the atmosphere should be reasonable, and you should have sensitivity where you are really pushing. So if you are trying to feed this part and you don't have spectral lines here, then I think it's not worth it to really push for that. So just try to focus on the regions where your spectral lines are sensitive to. Otherwise, that is worth it to look for observations where you have more spectral lines that are compatible between them than forcing very complex configuration. But try to experiment. Okay, so then I was here. Yes, we said that the sun is in fact more complex than the simulation. and then I said, this is an extra exercise. You can try, and if you try and you get stuck, just let us know, and I can explain it in next class. I think we are now fitting just ideal profiles, so there's no noise. But in general, your observations, besides being complex, they also have noise. So you can try to add noise to even in the simplest case, and try to invert again. And you see that the code will try to obtain a good fit, but depending on the noise level, the code or the chi-square computation can be affected by those noise values. So then it's not a problem of the code, it's that if your noise is too much, then you cannot really do a lot. If you are using IDL, I just recommend you to use this random n routine and add a noise of a given amplitude, for example, 1 × 10⁻³ all the profiles are normalized to the closest continuum. So then it's 1 ⁻³ of the continuum intensity. And I recommend you to add different value per wavelength point and per Stokes parameter, because I think this is reproducing a bit better what we have in observations. But again, if you feel that you didn't understand this part, just let me know, or just write a comment in Discord and we can check it. And then this is what I said about the amplitude. And then the second one is also try to experiment, as you know how to compute already response functions, and you have the atmospheres already in the SERF format. You can just run last week example and compute the response functions for the 3 Muran pixels that I showed today, and then check how the response function look in those cases. Yeah, I think yes. And next class, I think I will try to invert set profiles. As before, I think it's relatively easy to invert those profiles because they are space profiles, so there's no telluric contamination. Things are in general well calibrated, and also it's the same region that we have been using. So I think we will try to, and also the profiles, you can download them from internet. There's no requirement, so they are open data. So and also I will try to check, because today our measurement of accuracy was looking at the initial atmosphere. So we said, oh, the atmosphere that we are obtaining is close to the original one, so then it's a good fit. But when you're observing, when you're inverting observations, there's no way of doing that. So then your measurement of accuracy is your chi-square. So then I will explain you how the chi-square is computed in SERF, because the values are sometimes not so easy to understand based on the standard definition of chi-square. So I will explain you how it's computed. And then I will try probably in the next class to teach you how to transform pixels from, for example, from a Muran simulation using a subroutine of SERF, as I did for today's class. So how I took the initial simulation and I ran for 1 pixel their subroutine, and I got the optical depth and everything ready for running a synthesis or inversions. Okay, and then next class is next week on Friday, unless anyone has really strong problem, but I think we should keep Fridays as default date. So then next week will be the next one. So let's just maybe I stop sharing and let's start discussion. It took 60 minutes, 60 because we started at 5, so good. yes, we are on time. I will try to keep it like this because I realize that 90 minutes it's a lot, so I will try to have more sessions but shorter ones. I think it's better. So thanks, Hannah and Basilio, for the recommendation, and I think it's also better for you, so we can have even more time for questions. So
I think it may be worth for you, Carlos or Basilio, to explain a little bit more about the nodes. People might not be, for instance, why the difference between 60 and 61 is so big, because you basically use equidistant nodes and you have intervals that's n-1, the number of nodes, right? And so that's how it works. Maybe you can explain that. And also that the nodes are the points where you do the actual calculation, and the rest of the atmosphere is interpolation between the values that you obtain in the nodes. I'm not sure how well people are aware of those facts.
Yes. So Basilio, yeah.
No, you can explain that, okay? But the idea is that the code is evaluating the perturbation just at the nodes, and then it needs that the number of intervals of the atmosphere should be a multiple of the number of nodes, of the interval between nodes. That means that if you have an atmosphere with 61 points, you have 60 intervals. Then you can put as many nodes as you like, because 60 has a lot of divisor. Then you will have from 1, 2, 3, 4, 5. But if you put 60 points in your atmosphere, you will have 59 intervals, and this is a prime number. And then you don't have any possibilities, just one that is a constant and two that is in the two intervals. The number of nodes -1 should be a divisor of the number of intervals. Okay, this is the number of points -1. Okay, this is a little
yes. And the requirement that the nodes have to fall exactly on one of your depth points.
Yeah, exactly. Then I think that you can avoid problems if you are using the star and the automatic selection of nodes, but the behavior of the code is better when you allow first in 3, for instance, 2 or 3 cycles a fixed configuration, like Carlos one, and then a later one, a fourth one, for instance, allowing more freedom. In this case, you have the better of both solutions. You have 3 cycles in a fixed configuration and a later one with more freedom. And you can always choose the third of the 4 solution. Then you can say, okay, I don't like so many fluctuation. In these cases, I kept the third one instead of the 4th. Okay, if your solution is not good enough. Okay, because it has a lot of noise or wave behavior or something like that.
Yes. So Basilio, maybe you can also explain, because I said if you start with a given atmosphere and the code, for example, with one node move the magnetic field, and at some point it has to make it 0. Why when the field strength is 0, then the code cannot move from there?
Yeah, because the code works with relative perturbation, and then if in one node you have a 0 value of the magnetic field, then the code cannot modify that, because it multiplied by a factor. It's a 10% larger, but a 10% larger than 0, 0. Then this is the problem. I think we can solve that, because in case of velocity, as velocity can change sign, we are adding an offset to velocity. Then the code is working with the given velocity plus 7 kilometers per second, something like that. then the perturbation are relative to the actual value of the velocity plus 7 kilometers per second to avoid the changing by zero. We can do that for magnetic field, but making perturbation, but I have never did.
Yes.
Okay.
Well, I think I would say that it's fine like it is now. So just if we know that we should be careful on that. Because one option is that if you have a complex certification, then start also with a lot of nodes in the first few cycles. Then the code will not be forced to just move up and down. It will just be able. But I would say that these, for me, I think I prefer, as I said, conservative steps from constant and then analog. Move from there.
Another thing that I think is important is that in general, the flexibility or the degrees of freedom for temperature should be larger than the other. If you put 3 nodes in temperature, just 1 or 2 in velocity magnetic field, and so on. If you put 5 in temperature, 3 or 2 in the other magnitude, because the temperature is the more important magnitude parameter. Then the code needs more freedom for temperature that to get a good fit. It is better to allow more freedom in temperature than other quantities.
Yes. Okay. Yes, I think I put, so in the first case was like this. Sorry, in the second case, I think I had.
Yes, I had 2 or 3
and then 5 and then
exactly
5 and then 5, something like this. This is what we had.
Yeah, and the azimuth case is complicated because it depends only on the relation between Q over U. Then in general, there is very little information about azimuth. Then the stratification of the azimuth, if it's complex, it never is good to reproduce. Here we should be conservative and put a small number of nodes in azimuth because the spectral lines are really relatively insensitive to this.
Yes.
Okay.
Yes. So because this is it's difficult. Although if we add 180 here, it could be like a almost constant azimuth.
Yeah.
Okay. So thank you. So any additional question?
If you can hear me, I have a quick question.
Yes.
Is it possible to crop your model atmosphere to just include the optical depths that the line responds to? So in the case of this iron line you're looking at, a lot of the higher heights, i.e. your lower optical depths, it has no information on, but I assume the inversion is still placing a node there, and that is having an effect on your chi-squared value. Is it possible to just have a smaller, in essence, size, but then all of your nodes actually contribute to the usable data, if you know what I mean?
Yes. The idea is that I picked this atmosphere. In fact, the original one goes up to log tau -7. And I think I was just picking it because later I will use the same for desire, and then there we will have chromospheric lines. But if you only work with photospheric lines, then yes, you should probably around -4 or -4.5 could be a top boundary. It's good if you, for example, if you check the Muram pixels, if you compute response functions, you can have an idea of how quickly the response function can drop for all the scenarios that in principle you would have if you invert a sunspot. And from there you can build a model that, for example, stops in -4.5 or -5. The idea is that this one goes in steps of 0.1, so log tau 0.1. So if you start, for example, from -1 and you go to -4, then I think it's 49 points or something like that. So you could pick a number of 49, or if you go a bit higher, I think what Vasilio was saying, 61. So we had 81. So if you just remove 20, you would probably be in around -4.5, I think. And then this will be perfect for only photospheric lines. And I think it will be better than this one that I have here.
Yeah.
So yes, I think it is not only possible, I think it's recommended for the case when you only have photospheric lines. So
Yeah. Even if you are working, for instance, with the infrared lines at 1.6 microns, that there are deeper lines, you can go until -3 even, and you will have a good fit because you are working with photospheric and very deep lines, deep in the sense of height in the atmosphere. With these lines, stopping at -4 is a good solution also. -4, -4.8, depending on the number you like. Okay.
Yes. Yeah, so thank you. It was a good
Great,
question.
thank you. Yeah.
Carlos, isn't there a consideration about the electron pressure boundary condition? If you cut it too low, that's going to affect that, is it not?
If it's too low, yes, but I think we were trying to go to a case where the response function has dropped, and I think it's probably -4 or -4.5. So I would say that it's probably safe, but Basilio was nodding, so maybe Basilio has.
Yeah, no, it's a very good question because we never know about the boundary condition of the electronic pressure, and then you should put a lower value there. But in fact, you have not a big influence of the result. You can repeat your inversion, changing the boundary condition of the electron pressure, and you will see that there is not a really important change in the model. It will change a lot the geometrical height, the gas pressure, and the density values. This depends on the boundary condition of the electronic pressure, but the other quantities are nearly insensitive to this. This is in fact a problem because as the other quantities are insensitive to this boundary condition, you cannot determine this boundary condition. Then, in fact, if you are setting the electronic pressure boundary condition in deeper layers, maybe you are adding an uncertainty because if you are setting in very upper, you know that this is very small value. Okay, but in any case, the sensitivity of the profiles are so small to electronic pressure that it is marginal. Then it's not a problem. In fact, the question is that when you are working in a locked-out scale, the dependence of the electronic pressure is very small.
Okay, thank you.
Yes. Okay, so additional questions? Maybe go back to
you can always choose to put the boundary condition of electronic pressure or gas pressure or density. You can choose between different solutions. You can put there gas pressure at the surface if you don't put anything, or you can put if you put a negative value, the code consider that you are putting the condition in density, okay, a negative value, and then you can choose put gas pressure or nothing, or electronic pressure. Okay.
Yes.
If you put nothing there,
it's electron
blank,
pressure.
It's electron pressure. That is the value of the model. The last value of the electronic pressure of the model is considered the boundary condition.
So in this case, we are starting with init at, so it's this one. So it's taking the last electron pressure.
Okay, this is the boundary condition in this case. But you can.
Is to put
this you can put any other value. If you put a positive value there, this will be but you can play with the different value of the boundary condition. You will see that there is not a big importance in a big change in the result. Okay.
Yep.
Okay.
So Any other question? So was it okay today, or was a bit fast? Because I
think it was good.
okay. So then don't be shy. If you have just any question, just ask it, and if not, then of course we can go through those questions using Discord or just next week. Okay, so then if there's no question, then I will stop recording. And yes, I will stop the recording now.